Alright, in this video we'll look at numbers 6 and 7. So here we're trying to calculate the length of a curve, and it's given in this parameterized form, and it goes from 0 to 1, t 0 to 1. So as we look at that, we have an equation for the length. We sum up from the initial to the final positions of the derivative of x squared plus the derivative of y squared, and all that square rooted in it. That's pretty straightforward from kind of the Pythagorean theorem situation. So we take these two things, and if you look, we have the derivative here. This is kind of a chain rule effect here. If I take just the natural log of u, it's 1 over u, so I have 1 over that. And then the natural log of, or sorry, the derivative of the natural log gives us 1 over. Then the derivative of this square root gives us half of the square root of this to the negative 1. Or you could say 1 plus t squared to the negative half. And then we take the inside, that's the t squared, the 1 plus t squared. The derivative of that is 2t. So we get these 2's canceling. We get this 1 over the square root, and we got 1 over the same thing here. So you got a square root squared, so we're here, and we have the t. So that's where we get to that part. And then the tangent derivative of the tangent inverse is 1 over the quantity 1 plus t squared. So here, then we're just plugging our pieces in. And since they both have the same denominator, I went ahead and put those together. So this is the common denominator here. It's that part squared, of course. And then I have the numerator here, the t, it's squared. And then I have the 1 squared, which is still just 1, and they're added together. So that's where this comes from. And we're going from 0 to 1. So we have that bit, and of course you can see that this is going to reduce because there's a whole term here. So then we get 1 over that, and the square root of 1 is just 1, so we went ahead and put the square root just to the bottom. Now this is the this integral is the hyperbolic arc sine, so we can evaluate it that way, or its equivalent is the natural log of the quantity t plus the square root of the quantity t squared plus 1. So when we put those bits in, if I put in 0, we get 0 plus square root of 1, so that's 1, so natural log 1, that's all 0. And then the 1, here we get 1, and then square root of 2. So our length then is the natural log of 1 plus the square root of 2. And we'll take a look at that. Oops. Sorry. So here is our curve going from 0 to 1. You can see here, 0 to 1. We got our pieces in. And then this line here, from 0 up to this point, should be the same length as this curve. And you can kind of see, if we straighten that out, how that would look. And just to give you a better picture, you can kind of see how, if you made this into a radius, straighten it out into a radius, it might hit that circle. And I think we get that same situation there. Okay, so that was number 6. We'll look at number 7 now. Number 7, it says, a circular cylindrical can must have a volume of 108 pi cubic centimeters. Find the cost of the cheapest can if the material for the ends costs 20 cents and the material for the sides costs 10 cents. Now, based on this, the way it's stated, we would imagine the cheapest can is 30 cents because the ends cost 20 cents and the sides cost 10 cents. Let's assume that, for our purposes, that this problem means to say something like this: the ends cost 20 cents per square centimeter. So it's it's a per unit of material. So we'll call it 20 cents per square centimeter, and then same thing here. We get 10 cents per square centimeter. Okay, and then we're looking for the cheapest can cost. So looking at 7 here, we were told that the volume has to be 108 pi. We also know that the volume of a cylinder is pi r squared h. Here's our little cylinder, and then here's it cut out. I've got the tops, the ends, and then I slit the cylinder down the height and unfolded it, and you get a rectangle. Excuse me. Okay, so from this equation, if I solve for h, then I get 108 over r squared. Now my cost function should say that it's the material of the sides times the cost of those materials per unit, plus the material of the ends times the cost. So the material for the sides is this rectangle, right? Which is 2 pi r, that's the circumference, that gives us this length here, and then the height. And then of course it was, the sides are 10 cents per square centimeter. And then for the ends, we have 2 ends, so that's our 2, and then there's circles, so the area is pi r squared, and the cost is 20. So now our simplified form looks like this. I put in my h value here, put that in, simplified. Now of course we're trying to optimize, so we take the derivative. So I took the derivative here, I set it equal to 0. That means I want to find the point where my cost is no longer increasing or decreasing. I want it to, so in this case, I want to find a point where I've decreased as much as I can in my cost before I start increasing again. So I'm going to multiply these terms by r squared, and that's going to cancel that, and that's going to make that to r cubed. And then I'm going to solve for r cubed, which I did here, and that gives me an r equals 3. And then, so now that I have r, I can go ahead and put r back into my cost, and I get this situation here, to the -1, so that's divided by 3, and then it's 40 pi r squared, so I'm here, 40 pi 3 squared. So I get a 1080 pi, which is approximately 3,393 cents. Okay. And I think that gives us what we need for finding the cheapest cost. And of course, you could check to make sure this is a max or a min. Yes, you can do that, and I think you'll see what you end up with there. And so we will cover 8 and 9 on the next video.